So let's kind of look at dou L. You know, what are we indicating this by? So here if you see, right, so we are calling it as BIL, right, at any inlet layer. So suppose I take BI3, okay, let me say that, right, I need dou BI3, okay. Now dou L by dou BI3, so what is your L now? So L you had as, let's just go and look at what your L was. Can somebody tell me what was it? So L was, okay, 1 by 2 summation yi hat minus yi square, right, this is what you had. And therefore what will happen? So if you do dou L by dou BI3, right, so this will become, so 2 will cancel off, you will get yi hat minus yi, and then you will get dou yi hat by dou BI3, okay. And yi hat is nothing but, okay, but there is, I think, a simpler form. Let me just see, okay. Sometimes, right, people kind of get away with a simple form, but let's see. So yi hat is what? Yi hat is ai of, what is it? Just go back to that figure. Yi hat is ai 4, right? So yi hat is ai, 1 minute. That is the notation we use, no? AI4, no? So AI4, and AI4 itself, yeah. So AI4 itself, okay, yeah. I think so. What you do is, right, you play this trick that, well, it's simple, right? So what you do is you write this as dou AI4 by dou ZI4. Right, and then you write this as dou Zi4 by, because you need a direct relation between Zi and Bi, right. So write this as dou Bi3, because I mean eventually you want this with respect to Bi3, right, this is what you want, but yi hat is ai4 and ai4, I mean, and your relation is with Bi3 is directly related to Zi4, right. I mean that comes from that equation, right. Zi4 is in terms of Wij3s and Bi3s, right. And therefore, right, what happens? So this is nothing but f dash of Zi4, and Zi4, right, is in terms of, there is just an addition, right, plus Bi3, therefore that will be just 1, right, this last term is just 1, and therefore, right, so you can sort of write this dou L by dou Bi3, right, to be equal to y hat minus y I, and then dou yi hat by dou Bi3, which is f dash of Zi4. So again, right, this is something that you can evaluate, right, which means that you can change your Bi3. So how will you change your Bi3? You will say that Bi3, right, in the next iteration, right, and the next iteration will be Bi3 old and then minus some step size times dou L by dou Bi3. That's how you will use this, right, this gradient, right, in order to update. And so you just have to go back to that to the gradient descent, right. So theta n plus 1 is equal to theta n minus alpha times dou L by dou theta evaluated at theta equal to theta n, right. This is that equation. So just that theta can be weight, theta can be bias, and it is the gradient that you need to be able to evaluate, and theta equal to theta n means that whatever is the current value of B that you have for, within the, say, network, plug that in. Once you plug that in, you will get values for all of this, and which will then mean that this will be finally a number for you, right, and that you multiply and then you update your Bi, right, and then this is how you but of course, there are certain things like, how you do the training and so on. It's not like you push all the examples at one go, okay. So that we will come to, okay, once we get there. But for the time being, right, it is just enough that right, that we understand this. Now let's just look at what do you, so yeah, so I think this, let's just fill this up here. It's yi hat minus yi f dash of Zi4. What about, let's say, we also need dou L by dou Bi2, okay, and dou L by dou, okay, well, 1 minute, right. So see, I told you, right. So yeah, so there is actually a simpler form. See, okay, right, this is also correct. That's why I said it. There's no unique way to do this, but then, right, look at the simpler form. Yeah, because you want everything in terms of the right delta. So what you do is you do write this as dou L by dou Zi4 to dou Zi4. I thought that there was a simpler form, dou Bi3. See, go back to that diagram, right? So you're looking at right dou L by see dou Bi3, right? And it is simply dou L by dou Zi4, right, into dou Zi4 by dou C, right, Bi3, and yeah, exactly. No, the point is that what I'm saying is you do this because you want everything in terms of the delta. I mean, the other thing is also correct. Right? There's nothing wrong with that. Right? I mean, that's the way I would impulsively proceed. But then the whole idea is that right, you want to boil everything down to a delta rule, right? So what you do is instead of, so this is correct, but then this is not what you actually do, right? So what you do is this, and this you know is right delta I4, and this you saw here, right? Dou Zi4 by dou Bi3 was 1, and therefore it is simply delta I4. And this you can apply everywhere, right? Even at see Bi2 also. See, if I do dou L by dou Bi2, right, I can come straight away from this, right? So if I want, let's say Bi2, then what will I do? I'll say dou L by dou Zi3 and dou Zi3 by into dou Zi3 by dou C Bi2, right? Which then means that I'll again write see delta whatever, right? So I'll get delta 3 and then the other term is again 1. And therefore, right, in general, so in general, right, what you have is dou L by dou Bil will then be what? Dou I L plus 1. See, right, we do this one so that, we know as to how this works. Okay, that's all. I mean, not that, right, not that, this is when during implementation only you do this. But I thought it's worth, right, doing it just once. Okay, so you have like dou I L plus 1, okay, that is for dou L by dou Bil. Now I thought we'll also do maybe the matrix form of this. So which one shall we do first? So we have this equation, right? What do you have? You have delta I, where is that? Delta I L, right, is equal to summation j is equal to 1 to some, what is we write as L plus 1, then we wrote delta j L plus 1, and what was that? Wji, what was it? Wji L, and then into f dash of zi of L, right? This is what you had, no? So now suppose you wanted to find out, right, delta 1, let's say 3. Okay, I mean, I'm just doing it for just one case. Okay, suppose you wanted to do it for delta 1 3. That means if you go back to this diagram, always, right, always keep this in mind. Therefore, right, you are kind of looking at this delta 1 3, because assuming that delta 4 we already know. Okay, so then I equal to 1, right, and therefore, so how many neurons here, right? So your summation will go from j equal to 1 to, you're going to the fourth layer, right, L plus 1, therefore 2, right, j equal to 1 to 2, and then delta j. Okay, so then, right, what will this be like? So, right, let me just write this down. Delta 1 3 is equal to summation j equal to 1 to 2, right, 1 to 2, and then you will have delta j, L plus 1 is 4, right, and then W, then you have j, and then I'm looking at I 1, then L is 3, and then f dash of z, I is 1, L is 3, right. Therefore, if you expand this, what will you get? You get delta 1 4. All these are scalars, okay. So therefore, it's okay to multiply in whichever order, okay. So W 1 1 3 plus, okay, this let's put in a bracket, plus delta 2 4 W 2 1 3 into f dash of z 1 of 3, correct. Now, if you try to write down, I mean, right, so how many do we have like this delta in the third layer? You got 1 2 3, right. So therefore let's also write the next one. So can we write delta 2 3? What do you think? Right, that will be, can somebody tell quickly? Delta 2 3 will be delta 1 4 W 2 1 3 plus delta 2 4 W 2 2 3, right, into f dash of z 2 3, right, and then we can have delta 3 sorry, what happened? the delta j equal to 1 to 2, j is 2. Oh, no, 1 minute, I think, no, okay, no, this should be the other way around, okay, w I is 2, right, therefore, this will become w 1, 2, 3 and this will become w 2, 2, 3, correct, because j I, no, so see j is inside, so j is summing over 1 and 2, that is standard, but I is what is changing, right, from here to here what is changed is I, therefore, it will become w 1, 2, 3 and then w 2, 2, 3, this is okay. Right, and then what will happen to delta 3 3 going in the same vein, we will have delta 1 4 and then j is 1 first and then 1 3 3 plus delta 2 4 w 2 3 3 into f dash of z 3 3. Right? I mean just follow, right, whatever we have done. So what this means is that, right, I mean I could actually update the whole thing, right, together. I mean if I could actually, instead of writing them individually like this, what I could do is I could actually think about writing this as a vector, right, where I have, because each of these is a number, right. So delta 1 3, delta 2 3 and then let me say I have delta 3 3, and therefore, right, I need this to be expressed in terms of a matrix. And then, right, see if you go back and then see, right, what are the terms, right. So what are the terms that you have? You have actually delta 1 4 and you see, right, delta 2 4, right. So let us say I have delta 1 4 and delta 2 4 and then, right, you should have an element wise multiplication, right, because this is a vector. See here everything is a scalar multiplication, right. This is tricky. See here, right. So what you have is into f dash of z2, right. So it's equivalent to getting this matrix vector product, get a vector and multiply it, right, element wise, multiply the two vectors element wise. So what will that mean? So see, so your first, so you have like what, delta 1 3 should be w 1 1 3, w 2 3. Okay, W113 delta I, okay. So what will be the first two entries? W13 and I mean W213, right? This will be the first two entries, right? W113, W213. What is the next guy? Delta 23 is W12 and W22, right? Yeah, W123, W223, and then this will be W133, W233. Right, and here you will have a vector. So this is element wise multiplication, okay. This is element wise multiplication, and this will be like, what is it? What was that? F dash of zi, z13, z23 and z33, right. So then, right, see the standard notation for a weight matrix, right. Let's say suppose I call this as W3. I mean in that layer, right. This is, we are looking at the third, right. We are looking at L equal to 3, no. So this standard notation would have been like W113, W123, W133. This is how you would write it in a standard form, right. W213, W223. Wait a minute. W223 and then W233. This is how you would have written. Therefore, right, you can think of the matrix above as a kind of a transpose of this, right. So this is like 3 cross 2. Okay. This is how you would have written the standard weight matrix, and all your unknowns are these W's, okay. And so then, right, this if I call as delta 3 as a vector, right, then I have like delta 3, right, is equal to W 3, I'll write this as a transpose, right, W3 transpose, and then multiplying, and this multiplication is as a standard matrix vector multiplication, okay, not element wise. And then I can write this as, this is kind of, what will this be, delta 2, right, this, sorry, delta 4, this is like delta 4, see this is delta 4, this is in the fourth layer, and then you can just think of this as one vector that you get by multiplying, and then you have this one, I think let us call this as f dash of what is this, Z3, and all these places we have to know as to what it contains, right. I mean that let's assume that we know how many elements are sitting there, and you know, and the size and all, right, the dimensions and all are all correct, right. right. So in a way, right, so in general, okay, this I will just leave it to you, right. I mean, you can do it for any layer for that matter. So we can write this as delta L, right. So we can write this as WL transpose delta L plus 1, right, and the whole thing into f dash of ZL, right. So in a way, right, in one shot, because finally, right, during implementation, all people always like to have a matrix vector form, because so in one shot, right, I mean, you can get right, everything out. It's all one and the same, but sometimes implementation wise, right, it matters. I mean, how you write these things, right. So therefore, this is a matrix vector form. Okay, and this is called the right, delta learning rule. And the word propagation, right, when you say back propagation, so what you really mean is so the so let me just give you the exact okay, somebody said, right, that day that this came in 1986, right. So the exact this is the principle, right. Let me just write down. I mean, somebody asks you what exactly, I mean, this is all okay, the math part, but what exactly are you trying to do? Is a principled method, okay, involving chain rule, as you saw, to update the weights and the biases. Okay, when they say weights, I mean the biases also, to update the weights by back propagating the error, by back propagating the error, so that the network error reduces. Okay, right. This in a sense is what is this is the kind of summary of what actually back propagation is all about, and how you implement, right, is what we have seen. Okay, then I'll just leave it to you as maybe, right, as an exercise, or maybe, right, we'll just find out right away. So what do you think? Some of these are pretty straightforward. What do you think? I mean, if I had, let's say, what do I have here? Dou L by dou BL, where BL is again, right, I mean, so if you were to stack the BILs, right, at that place, right, as a vector, what do you think this should be equal to? We already saw, no, what was delta L or L plus, oh, is it L plus 1, no, delta L plus 1, not delta L, delta L plus 1, but as this one vector. Okay, so the bias part, right, is very simple if you write it in a vector form. I'll just leave this to you, right, as a small exercise. Okay, let me just ask you, so how would you write, let's say, W, let me see, right, somebody would be able to answer this. Let's say dou J by dou W, what do I have here? Okay, all right, so for this example itself, right, that we had, suppose I did dou J by C, right, or dou W3. Okay, let me just write down. So what I mean, I'll just write down this expression, right, which we've already found out, by the way, right. So Wij3 was actually delta I4 Aj3, right. This is what we had, no, right. I mean, right in the start, right, when we did dou J by dou Wij3, we got delta I4, right, Aj3, and therefore, right, I mean, if I try to see dou J by dou W113 again, right, depending upon what my I and J are running from. Let me just write down, I is running from 1 to 2, J is running from 1 to 3, okay, in this case, for that layer, okay, that's how it is running. Therefore, you will have overall 6 terms, right, W113, W123, W whatever, right, for the IJ combinations. And therefore, right, if you had to write it down, and dou J by dou W3, okay, so W3 is actually a matrix, right, this is that matrix that I wrote down, which was a 2 cross 3 matrix, right, and therefore, J is a scalar, by the way, right, L, right, we are using L, right, so L is a scalar, therefore, right, this will be a matrix again, right. What will that, how will you express it in terms of delta and Aj? Outer product, very good, right. So outer product, so this will be delta L plus 1 into AL transpose. Okay, this is just an outer product, right? So you have something like this, right? So you have this vector and column vector and then a row vector, right? So, and in general, right, this you can write down in general as dou j. No, okay, this is for L in fact. That's for L. If it was 3, it would have been delta 4, whatever, right? I mean A3 transpose. That's what it would have been. But in general, right, you can write it down, and these are all vectors. Okay, by the way, AL on top. L is always coming on top, right? So AL transpose. So this is an outer product. Okay, so what this kind of essentially means is that all these updates can be done. Okay, you can have as many layers as you want, and you can always back propagate, and and then sense what is the error, right, that you are making right now, and therefore how should the weights be updated so that the new weights are such that the overall error, if you think of that cost or landscape, right, that we had for the cost function, right, you are trying to traverse on that, and you are trying to traverse in a sort of a direction that will reduce the error, and which way to go is coming out of these equations, right, and therefore, and you can imagine, right, people are doing it over millions of weights and biases, so that way it's very powerful. For us, right, we just took a small example just to have some insights into how this works, but think about the way all this has been implemented, right? I mean, people have like 1 million parameters, 60 million, 70 million parameters out there, and the whole thing works so very smoothly, right? And there's a lot of work that's gone into actually building those packages and all, okay? So that you can do this quickly, and make use of all kinds of matrix properties and all in order to be able to do this in a fast manner, okay? Now, yeah. So is there anything else that I wanted to say in this? Okay, and then by the way, right, so what I will do is when we come to convolutional networks, which will come very shortly, right, we won't again solve all of this, right, this backpropagation. I'll just leave it to you, okay, because once you do it for MLP, I mean, that becomes in fact a simpler case of this, right, because I mean, you have convolution and all going on. Therefore, we don't want to sort of spend too much time, right? I just thought we'll do this once, so that, right, for those of you, right, who have not seen backprop, right, I mean, you'll at least have seen it once, right, in your life. Okay, so I think we will stop here.